Welcome to iSet Robotics, Into Gear on your mark. This is Unit 3, in which we will investigate problem-solving methods and apply them to the navigation of the robot. In this lecture, we want to discuss problem-solving methodologies such that you can apply them to find a solution to a given problem in a systematic way. Now, there are several methods to do this, but the method I want to present here, it's called Solbin. And it is presented in an Introduction to Engineering textbook called Thinking Like an Engineer. And Solbin basically is an abbreviation for the different steps that need to be performed in order to solve a given problem statement. So S stands for sketch. Sketch what you need to do, what's going on. O for objective and observations. Then we should list all our variables, where keep in mind a variable is nothing else than a placeholder for a value. Typically, variables have names, meaning full names. We also need to list all our equations, and then we need to manipulate the equations to come to a result. So let's see how we can apply Solbin to a robotics problem statement. So let's say we want our robot to move straight a given distance. So we have a start line and a stop line and a distance that I call d. D is a variable. So we measure the distance d between the start and the stop line, and the task for the robot is to start at the start line and to brake and stop exactly at the stop line. So you see, I've sketched what needs to be going on. And in the sketch, I've also put labels: start, stop, distance. And wherever possible, you want to put the names of the variables in your sketch too, because as you solve the problem, you will go back to your sketch. You can also add variables later and complete your sketch as you go along in solving the problem. So next, O, objective. Well, we need to program the robot to move exactly the given distance. So let's see what observations come to our mind. First of all, the problem statement doesn't specify if the robot should go forward or backwards. So we just need to make an assumption what we want to do. It's up to us. Let's say we want to go forward. Also, we know that in theory, the speed of the robot shouldn't matter. However, going slowly might be more precise because we're doing better with traction. The EV3 tank block needs to be programmed in rotations since it's a distance that's given. So the size of the robot wheels matter because with one rotation we go different distances if we have different sizes of the wheels. Also, the robot needs to brake at the end of the motion block. Want it to stand still at the stop line. We've learned by now that one rotation corresponds to moving forward by the circumference of the wheel. And we need to remember which part of the robot is on top of the start line, and at the end, exactly the same part of the robot needs to be over the stop line. You might have other observations to add, but these are the ones that came to my mind. So let's see what we have in terms of variables. List of variables. Well, you've already seen d as the distance the robot should travel. And I've just decided for this exercise we want the robot to travel for 50 centimeters. Next, we said we're going to program in rotations, and we know that one rotation moves the robot forward by the circumference of the wheel. So we need to measure the circumference of the wheel, and we call that variable c. And for the wheels that I've used, I've measured that circumference, and it's 17.8 centimeters. You can just take a tape measure and wrap it around your wheel, or you can take a string or ribbon, wrap it around your wheel, and then compare to a ruler what the circumference of your wheels are. So what we need in our program actually is the number of rotations that we are going to enter into the go straight block, and those we want to calculate. So you see that I have rows in my table here that are in bold. Those are the variables for which a value is provided in the problem statement. Then we have variables in italic. Those are the ones that we decided we need and that we need to measure. And then finally in red, the variable is marked that we must have at the end of our problem solving approach. In this case, it's the number of rotations, because that's what we need to enter as a parameter into the move tank block. Okay, equations are next. What equations do we need? Well, the circumference multiplied with the number of rotations will give us the distance that the robot travels. So on the top you see the equation written out, and then you see the equation being written using the variables. So that's the list equations step. And finally we need to manipulate our equations and at the very end enter values. So what we're interested in is not the distance, but we actually want to get the number of rotations. So we need to take the upper equation and solve for r as in rotations. And that's then the distance divided by the circumference of the wheel. So we need to take 50 centimeters for our example and divided by 17.8 centimeters, which is the circumference of my wheels. And that'll give us 2.81 rotations. See how the units cancel nicely. Centimeters divided by centimeters gives us a unit less number of rotations, 2.81. And then in the last step, you need to enter the 2.81 in your move tank block, as you see below. And finally download the program onto your robot and test it. Now you might say that this approach is way too complicated for such an easy problem statement, but let's assume I next ask you to exchange the wheels of your robot and want to know how many rotations you now need to go forward to cover exactly the same distance. The benefit of having manipulated the equations first and then entered values at the very end is that all you need to do now is measure the new circumference, and then you go and take the variable c here, and instead of 17.8 centimeters you enter the new value. Let's say the wheels are bigger, maybe 25 centimeters circumference, and then you get the required number of rotations immediately and you can enter it into your program. So let's look at another example. It's very similar. All the robot is going to do is it's going to move forward, and the problem statement is that we want to determine the relationship between the power that we enter for the motors and the speed of the robot. So the objective is to determine the speed of the robot as a function of the power levels of the motors. So you see the program there, it's same program as before. At the moment the power is set to 20 for both of the motors, so the robot will go straight, and it moves at the moment exactly from the start to the stop line. So in my sketch, well, I have my robot, and then again, like I have a start and a stop line, and it's not easy to measure speed directly. But what we can easily measure is the distance between the start and stop line. We call that d again. And we can measure the time it takes the robot to move from the start and stop line. And then we can use those two variables, distance and time, to determine the speed of the robot. So what do we need to pay attention to? So I've already said it's hard to measure speed directly. So let's measure time it takes the robot to move a known distance. And that's what I've graphed in my sketch. And I've also added the two variables, time t and distance d. Now, one thing to notice is that at the beginning of a motion, the robot accelerates, and at the end, it slows down, so it doesn't move at a constant speed. So if we want to kind of like know the speed for a power level, that's kind of assuming that that acceleration has already happened and that the robot hasn't slowed down yet. So we cannot directly take our approach from the last experiment, the last problem statement, start at the start line and stop at the stop line, but we should actually start our robot before the start line such that when it crosses the start line, it already has its constant speed. It goes beyond the stop line. And then all we need to do is we need to measure the time from when it crosses the start line until when it crosses the stop line. Also note that we have to repeat that experiment several times with different power levels. And for all these different times, we can keep the number of rotations constant because the distance won't change. We already know that the speed increases with the power level. What we want to know is kind of like how does it increase with the power level, but we know that if we pick a higher power, then the robot will move faster. And we need to pay attention to our distance. How far do we want the robot to move? Basically, we want to pick a distance to where we can measure time reliably for all different power levels from the slowest to the fastest mode. So you don't want to make it like 10 centimeters because then it's very hard to measure the time at the highest power. Okay, list of variables. We have, again, the distance that the robot should travel. And this time it's not in bold, but it's measured, so it wasn't given, but I picked it. So you just pick whatever value you want. I picked 1 meter. Circumference of the wheels is again c. I used the same wheels as before, where the circumference is 7.8 centimeters. We need to enter into our program the number of rotations for the move tank block. So those first 3 are exactly the same as the ones we've seen in our previous example. Now, however, we also need to pay attention to the power level of the motors, and that's what's basically given to us, thus in bold. Want to do power levels 10, 20, 30, up to 100. We're not going to do power level 0 because then the robot stands still and it will never cross any of the lines. T sub p is what we call the time at power level p. So we do different power levels, that's our variable p, and then for each of the power levels we need to measure the time. And finally, v sub p is the speed that we calculate for each of the power levels based on our measurements using some calculations. So what are the equations we need? Well, we need to figure out how many rotations we want to use in the program again. We use the same equation as before. Circumference times rotations will give us the distance the robot travels. Now, we don't want it to be exactly the distance between the start and the stop line, but I've chosen 1.5 times the distance because I said we're starting a little before the start line and we'll stop after the stop line to ensure that between start and stop line, the robot will travel at constant speed. You can also pick 2. Basically, it needs to be a number that is larger than a factor of 1. Now, our second equation helps us with determining the speed. So speed times time will give us the distance, or with variables v sub p times t sub p equals the distance. The distance is always the same for each power level, thus it doesn't have a subscript, but my velocity and my times vary with the different power levels p that I'm using. So we take these equations, we manipulate them to get the number of rotations. And in my case, where I want to have a distance of 1 meter between my start and my stop line, I have 150 centimeters divided by the circumference of my wheels. So I need to enter something around 8.5 rotations in my programming block. And then we need to calculate the velocity or the speed, v sub p, and that one we get as the distance divided by the time that we've measured at power level P. Okay, so now we need to perform the experiment. We know everything that we need to measure and we need to tabulate our measured values. So we pick different power levels. Here I've just picked 10, 20 and then went on in steps of 20, so 40, 60, 80, 100. You can also kind of like go all the way in steps of 10, so 10, 20, 30, 40 and so forth. For each power level you need to measure the time TP and fill it in next to the power level. And then you calculate the speed by taking your distance and divide it by the time and enter the speed. And then you repeat it for all the different power levels. And then you need to come up with a conclusion. We already knew at the beginning that the higher the power level, the faster the robot. But now we wanted to know how much faster. So if I increase my power by a factor of 2, does that mean my speed also increases by a factor of 2? If I increase my power by a factor of 10, so I compare power 10 with power 100, does it mean my speed increases by a power of 10? So you could actually kind of like graph your speed over your power level and come up with a conclusion there.